In this presentation on real numbers, we are going to discuss certain problems related to Euclid's division lemma. So the first question we have over here, it is using Euclid's division lemma, show that the square of any positive integer, it is either of the form 3m or 3m plus 1. So in this question, we are interested in the square of any positive integer. So suppose we are saying that n be an arbitrary positive integer. Now looking at these values over here, it is 3m and 3m plus 1. It means we are interested in the divisibility of n by 3. So we are saying on dividing n by 3, by using the Euclid's division lemma, we will have some quotient q and the remainder r, such that we can write this n is equal to 3q plus r, where the value of r we are saying it is greater than equal to 0 and less than 3. Now as we are interested in the square of any positive integer, so n is, we are considering the arbitrary positive integer, so we are going to consider the value n square. So when we square this term, we will get it is 3q plus r whole square, and that is equal to 9q square plus r square plus 6q r. Now we have three cases corresponding to the values of r. First case we have when r is equal to 0. Second, when r is equal to 1. And third, when r is equal to 2. Now corresponding to this first value, r is equal to 1, the value of n square that we will have when you substitute r is equal to 0 in this equation, we have this value of n square. When we substitute r is equal to 0 in this equation, we will get n square is equal to 9q square, and we can write this 9q square as 3 into 3q square. Now if we substitute this 3q square as m, then what we obtain, that n square is equal to 3 times m. In the second case, we are saying when r is equal to 1, the value of n square will be, it is equal to 9q square plus 1 plus 6q. When we substitute the value r is equal to 1, we will obtain this value. Now this term we can write it in the form, when we take 3 common, we are writing it in the form, this is equal to 3q square plus 2q. We are talking about this term 9q square and this is 6q. From these two terms we are writing 3 common. Now the only term we are left over here, it is this one. So we are saying the term we are left over here, it is this term plus 1. So we can write this term as, this term we are writing, it is 3q square plus 2q plus 1. We are having this term, and if we write this 3q square plus 2q as m, we will get this value is equal to 3m plus 1. Similarly, when we are talking about the third case, when r is equal to 2, we have the value of n square is equal to 9q square, then r square will be 4, and 6qr, this will be 12 times q. Now from these three terms, we can write 3 common. How we are writing 3 common? We can write this 4 as 3 plus 1. Now from these terms, from this term if we write 3 common, we are left with is 3q square. We have written 3 common, we are left with this 3q square. Then we have plus 4q plus 1 plus 1, we are writing it in this form. And this value, we are talking about 3q square plus 4q plus 1. When we substitute it equal to m, we are getting that this value is equal to 3m plus 1. And this is what we have to prove. We are saying that if n is any arbitrary positive integer, then n square, it will have this value. Now corresponding to 3 different values of r, we are saying either n square is of form 3m or n square. In rest of these two cases, the n square is of form 3m plus 1. So this proves the result that square of any positive integer is either of the form 3m or 3m plus 1. Now the next question we have is, using Euclid's division lemma, show that cube of any positive integer, it is of the form 9m, 9m plus 1 or 9m plus 8. So we start this proof by considering that let n be any arbitrary positive integer. Now if we look at these terms, it is this value, it is 9m, this is 9m plus 1 and this is 9m plus 8. So it seems like that we should use the divisibility by 9, but in this question we are interested in the value of cube of any positive integer. So we will see in this proof that if we consider the divisibility with 3, it will be sufficient for this proof. I'm again explaining this thing. We are saying that this value, it is 9 over here, it is 9m, 9m and 9m. So it seems like we should check the divisibility with respect to 9. But because we have to calculate the cube of the positive integer, so we will see over here that using the divisibility with respect to 3 is sufficient for this proof. So we are saying on dividing n by 3, we will have, by Euclid's division lemma, we will have two integers q and r such that n is equal to 3q plus r, where this remainder r, it is greater than equal to 0 and less than 3. Now we are interested in the cube of this positive integer. So it means if we calculate the cube of this integer, we are talking about n cube, we will get the value, it is 3q plus r whole cube. This is the value of n that we have. And on cubing this term, taking the cube of this term, we will have this is equal to 27q cube plus r square cube plus 9qr plus 3q plus r. Now if we adjust the terms, we obtain it is 27q cube. Then we have the term 27q square r. Then we have the term 9qr square. These two terms are corresponding to this value. And the last term that we are left over here, it is plus r cube. The last term we get, it is plus r cube. And what condition we have over here is that r is greater than equal to 0 and r is less than 3. So again we have three cases over here. First case is when r is equal to 0. Second is when r is equal to 1. And third case we have when r is equal to 2. So if we substitute these values of r in this equation, in this value of n cube, in the first case we are saying when r is equal to 0, we will have n cube that is equal to 27q cube. We have substituted r is equal to 0 and we can write this is equal to 9 times 3q cube. And if we substitute this 3q cube is equal to m, we obtain that this n cube that is of the form 9m. So this is our first thing we have to prove, that it is of the form 9m, n cube, that is cube of any positive integer, either it is of the form 9m. So we are saying n cube, it is of the form 9m in this case. In the second case, we are saying when r is equal to 1. So if we substitute r is equal to 1 in this equation, we obtain the value, it is n cube that is equal to 27q cube plus 27q square plus 9q plus 1. This is when we substitute r is equal to 1. Now from the terms in this bracket, from all these terms we can take 9 common. So we obtain the answer in the form, it is 9q common, and we are left with this term. It is 3q square plus 3q plus 1. And if we substitute, and we have plus 1 over there. Now we are saying if we substitute this term q square, q into 3q square plus 3q plus 1, if we substitute this value is equal to n, we get that n cube, it is of the form 9m plus, and this is the second term over here. We are saying it is 9m plus 1. And in the last case, we have when r is equal to 2, the value of n cube, that will be equal to 27q cube. Then we have 54q square. Then we have plus 36q, and then we have plus 8. Now again, if we look at these terms over here, these all terms, these are multiple of 9. So we are saying that we can take 9q common, and we obtain it is 3q square plus 6q plus 4 plus 8. Now if we substitute this value, we are saying q into 3q square plus 6q plus 4. We substitute this value is equal to 4m. Then we are saying that n cube, it is of the form 9m plus 8. So we have obtained these three values. We are saying if n is any arbitrary positive integer, then cube of that number, that is either of the form, we are saying n cube, either it is of the form 9m, or n cube it is of the form 9m plus 1, or n cube it is of the form 9m plus 8. And this is what we have to prove. Now the next question we have is, show that one and only one out of n plus 1, n plus 2 is divisible by 3, where n is any positive integer. So it is being given that n is any positive integer, and we want to check the divisibility of n plus 1, n plus 2 with respect to number 3. So we start solving this problem in this way. We are saying that on dividing this integer n by 3 by Euclid's division lemma, we have two numbers q and r. Q will be the quotient and r will be the remainder, such that n is equal to 3q plus r, where this remainder, it is greater than equal to 0 and less than 3. It means that the possible values of r, they are 0, 1 or 2. Now corresponding to these values of r, the values of n will be corresponding to 0. When we substitute r is equal to 0, we will get the value, it is 3q. When we substitute r is equal to 1, we get the value, it is 3q plus 1. And when we substitute r is equal to 2, we get the value, it is 3q plus 2. It means we are saying that if n is any positive integer, then it is either of the form 3q, or it is of the form 3q plus 1, or it is of the form 3q plus 2. So if this number is of the form 3q, first case we are taking over here, it is if n is equal to 3q, then clearly this number n itself, it is divisible by 3. Next, we are saying if n is of the form 3q plus 1, then clearly n is not divisible by 3. But if we calculate the value of the number n plus 2, the answer we obtain, that is equal to 3q plus 3. If we take 3 common, you can write this is equal to 3 times q plus 1, and this number is divisible by 3. We are saying it is divisible by 3. Now the third case we have, case 3, we are saying if n is equal to 3q plus 2, then this number 3q plus 2, it is not divisible by 3. It is plus 2 over here. So if we calculate now the number n plus 1, we are saying it will be equal to 3q plus 3. We have, this is 2 over here. We are saying n plus 1 we are calculating, it is 3q plus 3. And this number 3q plus 3, that we can write it in the form 3 times q plus 1. So we are saying that it is divisible by 3. So what we have proved, suppose we are talking about, say, the number 7. We are taking n is equal to 7. Then clearly n is not divisible by 3. We are saying 3 does not divide 7. Now if we calculate the value n plus 1, so n plus 1 will become 7 plus 1 is equal to 8. So what we get in this case is that 3 does not divide n plus 1. If we calculate the value n plus 2, we will have the value 7 plus 2 is equal to 9. We have 3 divides 9. So this is what we have proved in general, that if we consider any positive integer n, then one of the numbers n, or n plus 1, or n plus 2, one of these three numbers, it is divisible by the number 3. Now the next question we have is, show that one and only one out of the numbers n, n plus 2 and n plus 4 is divisible by 3, where n is any positive integer. So we proceed in the similar way as we have proceeded in our previous question. So we are saying that n is any positive integer, and on dividing this n by 3, we will obtain by Euclid division lemma, we will have two integers q and r. Q will be the remainder and r is q will be the quotient and r will be the remainder, such that we are writing n is equal to 3q plus r, where the value of this r, it is greater than equal to 0 and less than 3. So the possible values of r that we have, it is 0, 1 and 2. And corresponding to these values of r, we will have the values of n, that is 3q, 3q plus 1 or 3q plus 2. So we are talking about three cases. In the first case, we are saying if n is equal to 3q, then clearly this number n itself, it is divisible by 3. Next case we have is, if n is equal to 3q plus 1, then this number, it is not divisible by 3. But if we calculate the number n plus 2, we will get this is equal to 3q plus 3, that is equal to 3 times q plus 1. So we are saying that if the positive integer n is of the form 3q plus 1, then n plus 2 will be divisible by 3. And the third case we have it is, if n is equal to 3q plus 2, then this n is not divisible by 3. We have n plus 2 will not be divisible by 3. If we calculate the value over here, say we are talking about the value n plus 2 we are calculating in this case, the value we obtain, that is equal to 3q plus 4. You can write this is equal to 3q plus 3 plus 1. So this number is also not divisible by 3. Now we are talking about the number, it is n plus 4. And we obtain that in this case, the value of n plus 4 we obtain, it is 3q plus 6. And we can write this is equal to 3 times q plus 2. And it is divisible by 3. And this is what we have to prove, that one and only one out of n, n plus 2 and n plus 4 is divisible by 3.